Welcome to the presentation of our Data Mining Techniques term project. In this project, we looked at the City of Boston's annual employee earnings reports. Each earnings report stores data aggregated by the Office of Human Resources. It records every employee's name, department, job title, and the quantity of pay they received in specific categories, for example, regular pay, overtime, and workers' comp. The data that we had access to ranged from 2011 to 2019, and after initial pre-processing, we were left with a little under 200,000 instances. We merged this data with demographic data gotten from Simply Analytics. This demographic data included the median income and race breakdowns by percentages by zip code for a specific year. After merging the two data frames, we were left with 130,000 instances, around a 65% retention rate from our original quantity of instances.
Hi, my name is Shagun, and I will be speaking about the basic statistics and linear regression for our Boston Employee Earning Report analysis. So for basic stats, what we did was we split the data by year to run the basic stats so we can compare them over time, so from 2011 to 2019, 9 years. Each year had a very even number of data instances. There was no year that had a big spike or big drop in the number of rows available. The lowest amount of data instances was for 2011 when we had 13,607 instances, and the highest number was for 2019 when we had 14,838. And so this was good because this provided us about equal sample size for each year. When we did data analysis on this data, one thing we looked for was the top 10 highest paying jobs each year, just to see if there was any trends we could find or if there was any differences in the jobs, the highest paying jobs. So one thing we saw was there are very big similarities between the highest paying jobs each year. Multiple jobs make multiple appearances on the top 10 list. For example, superintendent was actually the highest paying job, #1, for 5 different years: 2011, 2012, 2014, 2016, and 2017. Similarly, commissioner was also the highest paying job for 3 years: 2015, 2018, 2019. And some other jobs that made multiple appearances on the list were president and mayor. So the trend that we saw was there was a lot of similarities between the highest paying job across the 10 years. We also looked at the average regular pay for our Boston employees. So there were many different types of pay fields, pay features in our data that we could have used. We chose regular pay because this was the most consistent across them all. Other features had employees with no earnings of that type, for example, with overtime or with education incentive, while regular was the bulk earning of all the employees. So that's why we chose regular. The regular pay also rose for Boston employees over these 9 years. So in 2011, the regular pay was $50,581 versus in 2019 it rose to $60,602. And I'll talk about this more later. So here we can see the regular pay over time plotted as a linear regression plot. We chose to use linear regression just to see if there was any correlation, if we could find a trend for the average regular pay over time. As you can see on the left, the regular pay increases, which we already saw, and it increases pretty consistently year to year. The only time when the average regular pay actually decreased was from 2011 to 2012, when it actually went down very slightly. Some other years it only went up a very little bit, for example 2012 to 2013, but over the 9 years the average pay went up about $10,000, from $50,000 approximately to $60,000 approximately. This box and whisker plot shows the statistics for regular pay across the 9 years. As you can see, the 25th percentile and the outliers changed significantly, for the outliers at least. So the outliers, as you can see, it actually increased in that 1 year. It spiked in 2018, where there were 3 outliers that earned a lot more than than the other employees. But the medians and the percentiles were actually fairly similar. So the median, which is the green line, stayed pretty consistent, as well as the percentiles themselves. One of the models we chose to run was linear regression. We chose linear regression as one of our models because we wanted to see if there was any correlation between the regular pay and overtime pay. Um, so this was interesting because we could find if an employee was lower paid for the regular pay if they had a higher chance of earning more overtime, less overtime, or if there was no correlation between them at all. So we ran this linear regression for regular pay versus overtime pay for each year, as we did with the basics stats, for 2011 to 2019. The coefficients for linear regression ranged from 0.08 to 0.12 from the 9 years. We got an R squared score of 0.10 to 0.13 for the 9 years, and we got residual sum squares that were very large, so they were in the millions, as you can see the numbers on the screen. The variance we also got was 0.11 to 0.14 from the 9 years. So the coefficients and the R squared scores did increase over time. So they started off as the lower end of the range listed, and they ended as the higher end of the range listed. And so this could suggest some correlation that that the correlation between regular and overtime pay increased over time. But because these values are so small, we can't conclude any statistically significant findings from linear regression between regular pay and overtime pay because the values are so small, and this means there is no statistically significant finding.
My name is Zach Manfredi, and I'll be discussing the decision tree classifier model that we implemented on our dataset for this project. We decided on this model in order to determine how accurate the algorithm is at correctly predicting each sample's income category bracket that was derived using a two primary component PCA on the Employee Cumulative Earnings Report. We were curious to see if and what values of primary components were overwhelmingly clustering samples in certain income brackets. Based on the results on the decision tree graph visually, it is very clear that samples assigned to lower income levels were clustered towards the left-hand side of the graph, while samples clustered to higher income levels were clustered towards the right. Notably, all 40 samples with a principal component 1 of 0.095 or lower and the principal component 2 of 1.405 or lower were clustered to the lowest income bracket, which was less than 10,000 K. Also, we noticed that when the principal component 1 was 0.86 or higher, all samples were assigned to one of the top 3 highest income brackets, which would be 90K or higher, regardless of what the value of the principal component 2 was. When running the classification report on this, it was able to yield a 72.9% accuracy score.
Hello everyone, my name is Surendra, and for this project I worked on two models. One was k-means clustering and the other one was decision tree classifier. Today I'm going to talk about k-means clustering model that we worked on for this project. So basically we wanted to use k-means clustering to find any grouping between certain zip codes and income based on the data set, and in order to do that we used regular income and zip codes from the data set. If you look at the graph here, the k-means clustering, it doesn't really give you any insight on any sort of like clusters based off incomes or zip codes, so it didn't really provide us with any information for the problem that we are trying to solve with this project. So basically if you look at this, the certain values at the bottom of the graph are basically income levels that we have in our data set. We have about 200,000 datas with different income levels, and we ideally wanted to cluster all of them based off certain zip codes, but then we had a lot of zip codes which was very hard to group them together into one certain zip code and make clusters around them with certain level of incomes. So it didn't really work for this model, didn't really work for us for this project. And in the future, we want to use this model again for better outcomes. And in order to do that, what we want to do is we want to use only maybe like 10 zip codes that are grouped for specific incomes. And in that sense, it will be easier to use this model so that we can build around the clusters of income and zip codes to see certain income levels are lied at certain zip codes. So that's what we plan to do. But for this project, it didn't really work out, this modeling. So yes, that was my part, and thank you so much.